All right, let's do a graph problem in CSES. Cycle finding. So what's going on here? We're given a directed graph, and we should find out if it contains a negative cycle. And if it does, we should actually print out the cycle. So standard input format, the edges are weighted, right, from positive or negative. I'm looking for a negative cycle, which means sort of a path around the graph, such that you start and end at the same place, and the total sum is negative. So for example, 1 to 2 gives you +1, 2 to 4 gives you +1, and 4 to 1 gives you -3. So if you follow this path around the graph, you start at 1, you end at 1, and your total sum is -1. So that would be a negative cycle, right, because the sum is less than 0. So we want to find any of those, and if there aren't any, then print no. 2,500 vertices, 5,000 edges. Weights on the edges are between -1 billion and 1 billion. So how do we do this? This is another Bellman-Ford problem, as you should know from the fact that we want a negative cycle, right? Bellman-Ford is all about negative cycles. So finding out whether or not we have a negative cycle is just sort of straight Bellman-Ford, right? And to remind you how that works is you relax all the edges n times, and by relax I mean you say that if following this edge, right, you're going to keep track of a best distance to all the nodes, and if following this edge gives you a better path to 2, right, that is the distance to 1 plus 1 is less than your current best distance to 2, then mark down a new best distance to 2, which is the distance to 1 plus 1. You just do that for all the edges n times, and then you do it one more time, and if any of the distances decrease, then there is a negative cycle. And the reason why that was that after you've relaxed all the edges, say k times, then you found the best distances using paths of length at most k. And if there's no negative cycle, the best path is going to be of length at most the best path, if there's no negative cycle, is going to be of length at most n-1, right? Because there's no point in repeating a vertex if you don't have a negative cycle. And so if you relax the edges n plus 1 times, and the distances are still going down, then one of the best paths must have length more than n, which means it must repeat a vertex, which means it must have a negative cycle, or it wouldn't be better than a shorter path. So how do we actually find the negative cycle, given that we know that there is one? This is like not standard Bellman-Ford. I actually had some trouble figuring out how to do this. But the solution is, so the vertexes whose distance decreases during the n plus first iteration, those vertexes must at least be descendants of some negative cycle, right? Because we said that the length n plus 1 path through them goes around some negative cycle. So what we're going to do is we're going to keep track of like parents of every vertex, right? So when an edge decreases the distance to some vertex, update the parent. Say that the sort of start of that edge is the parent at the end of that edge. And if we walk back far enough from any vertex whose distance decreases during the n plus first iteration, we're eventually going to get to the cycle. And then we can walk around that cycle to print it out. So I'll show you. It'll be easier to show that in the code more precisely. But that's the idea. So let's give it a try. You notice that I have not solved this one yet, unlike most of the other ones. So hopefully there's nothing tricky that I missed here. But let's give it a go. So this is called cycle finding. So we read in n and m. And now we read in the edges. And by the way, the edges are one way here, right? It's a directed graph. That means that the edges are one way. As usual, they are one indexed in the input, Actually, because it's Bellman-Ford, we don't actually need to keep track of like the edges. Normally you keep track of like which edges are coming out of a vertex, but for Bellman-Ford, we just need to keep track of just which edges there are. We don't really need to sort them by vertex. Sure. Okay, so for n+1 iterations, do it that way. That's probably clearer. For each edge, we'll relax it. So if if dA plus C is less than dB, so we need to keep track of a parent, and dB equals dA plus C. A parent and a best distance. Should be plenty. There's maybe a potential issue here, which is there's not really any like start vertex. I believe if we just start everything at infinity, it will still like end up decreasing for the negative edges. So I think we will end up finding a negative cycle this way. It's a bit odd, right? Even though we're not like calculating a distance from any particular vertex, but we'll see. Also, if so if t is n+1, then we can use this vertex to find a negative cycle. So if cycle is still -1, then there was no negative cycle. So print out no. Otherwise, print out yes. Who's supposed to print out the length of the cycle? No, just the cycle itself. So first we're going to walk it back n steps. This is to guarantee, right, we might not be on the cycle right now. We just have descended from the cycle. So if we walk back n steps, though, we are going to be in the cycle, right? Like we've walked through then all the vertices in the graph. We have to have walked back far enough to be on the cycle. Okay, and now we're going to walk around until we get back to where we started. This is a do-while loop because I want to move one square before I start checking, or we'll just immediately stop. And we should also print the, we want to print like the, one gets printed twice here. So that's what this is doing. This is putting the starting vertex at the end. There's one tricky thing here, which is we are walking like backwards along the cycle, right? We're walking to the parents, but the edges are directed, so we have to go forwards. So we're going to print out the cycle in reverse order. So instead of starting from 0, we're starting from cycle.size -1, the last thing, and we're going backwards. It's -I. And that should be it. Okay, yeah, we need some include stuff. So IR scheme for IO, we need vector. We need tuple because we're using that. Okay, I said LLL was a tuple, right? This is the type of the edge, right? This is this type. Okay. I should, we were 0 indexing, we should go back to 1 indexing. Okay, so 4, 1, 2, 4. That's the same as what they printed out. It's just that we started at 4 and they started at 1, but 4, 1, 2, 4 is valid. So let's see if this actually works. Cool, so that does work. That's nice. I was a little bit worried. So yeah, we do Bellman-Ford, and we find out if some vertex decreased its distance on the n plus first iteration. If there was no such vertex, then there's no negative cycle. If there was a vertex, then there is a negative cycle, and we can use that vertex to find the cycle. So we might not actually be on the cycle, right? Because the shortest path to the vertex could be going around the cycle and then going off somewhere. So we need to step back a bunch of times to make sure that we get onto the cycle. N times is enough, right? Any path, there's only n vertices in the graph, so you must be on the cycle at this point. And then we can just walk around the cycle and print it out. So yeah, that's the problem. The slow part of this is the Bellman-Ford. So that's b times e time, right? It's very obviously true. This is b times, or b plus 1 times, and this is e times. And this part is fast, right? This is just like 2n steps. So yeah, that's how you find a negative cycle with Bellman-Ford.